Welcome to lecture 23. This is our second intermission, taking a little break between Unit 3 and Unit 4, having completed our coverage of classical physics and getting ready to start Unit 4. Also, there are timed assessments taking place this week. In the first half, we go over some of the essay questions from Unit 3. Again, these are the multimedia-oriented essay assignments that we used to have. Because some of the essay timed assessments you will see may be related to some of these essay assignment questions and scenarios, I thought it would be good to give you some chance to see these. In the second half of this intermission, I wanted to tell a story of light. Light as a concept, idea, some primordial thing that you have seen, thought about, and have heard others talk about, both in scientific and non-scientific context. I want you to talk about how our understanding of light has grown through the era of classical physics, the time of Newton, Kelvin, and other physicists who have worked on our understanding of thermodynamics and electromagnetism. And I want you to preview the role that light will play in our understanding of modern physics, in particular as we introduce special relativity and quantum mechanics. We will start Unit 4 next week. Now, we first look at Unit 3's old essay assignments. Okay, so let me go through the Unit 3 essay assignments the same way I've done for Unit 1 and 2 last time we had this intermission. So we have 4 essay assignments from Unit 3 on chapters 8, 9, 10, and 11. So I'll go into the assignment just to play brief muted segment of the video, because these assignments were oriented towards multimedia content. They all have some sort of video that people would watch, and then conceptual questions that they would answer. And again, the reason this might be relevant is because there are some essay timed assessment questions which assumes that you have had opportunity to do these assignments and consider these scenarios. So I'm gonna start out with just chapter 8, this peer grading thing that shows the model answer. So I'll have this on this side, and let me go into chapter 8 essay assignment on thermal physics or thermodynamics. Again, I will start by playing the video. For copyright reasons, I won't play the whole thing, and it'll basically play muted. The Stirling engine, I could play the whole thing. That is my video, so there's no copyright reason. But let me, so heat engines, the first video is from FSE Learning, explaining basic features in the working heat engines. And the second video is a demonstration Stirling engine. This is the link to Wikipedia about Stirling engine. So let me start by kind of showing what this FSE e-learning video is showing about heat engines. Let me turn on closed captions. So it's some basics about thermodynamics, the flow of heat from hot to cold. And this is an example of a Stirling engine that operates with the 2 temperature reservoirs. The bottom plate is the hot tea. The top plate being exposed to the air, that's the room temperature. And between those 2 thermal reservoirs, it's enough to run this small demonstration heat engine. I think that might be it. Yeah, and this can also work the other way. Now the top plate is the hot room temperature where heat comes in, and the bottom plate contacting ice is the heat output. That's the low temperature reservoir now. And I think the way this is built, the direction of the wheel spinning, it depends on that direction. I guess doesn't have to be, it can be. Here it is. Yeah. So this is the video that has more of the kind of explanations of a heat engine, and this is just a demo video. Let me first see how long it is. If it's not too long, I might play the whole thing of it. I do see it almost 4 minutes long, so I might not actually play the whole thing. But here, let me turn the sound on and just play for a bit. Yeah, it almost sounds like a train or something. This is the old demo. I think I have a, when this one broke, I think at some point the gas was leaking too much out of these pistons. So I got a new demo. I think I edited the demo video of that into your lecture videos that you have seen. So from here on, if I let it run, it'll just show the running of this the Stirling engine, and I think at some point later I blow out the alcohol lamp, and it'll still continue to work for a bit while this hot thermal reservoir remains at the relatively high temperature. So the operation of the heat engine actually, it tends to cool this hot thermal reservoir because it's helping kind of transfer heat into the cold reservoir as it operates over a cycle. So that's the demo. Did it get stuck? Oh, I think I blew out the light a while back. Yeah. I blow it out, and then it continues to running for a bit until it eventually comes to a stop when this hot thermal reservoir and kind of dies down. And then once it comes to a stop, then pushing it again won't really get it to move because this is again not hot enough. That's actually what the thing at the beginning was. It took about a minute or two for this hot end to warm up. So now that I've relit the alcohol lamp, it doesn't take as much of a warm up time. It'll run almost instantaneously. Yeah. So that's the video. Alright, so with those demos in mind, I'm gonna do the same thing as before. I'll read the questions one at a time, and then I'll read the answers one at a time. Okay, so the questions. Number 1, explain in a short paragraph what a heat engine is and what it does. Make sure your explanation includes A, what is the purpose of a heat engine? B, what does a heat engine need to achieve the purpose? And C, what limits how well a heat engine can achieve that purpose, quote-unquote efficiency. And this is a kind of an open-ended question. This is the model answer of that open-ended question, but people could answer it differently. Okay, so the question is, explain what a heat engine is. Model answer. A heat engine is a device designed to do mechanical work using flow of heat from a high temperature reservoir to the low temperature reservoir. The way heat engine does work is consistent with conservation of energy. In each cycle, the heat engine takes in some amount of heat, QH, from the high temperature reservoir and releases QC into the low or cold temperature reservoir. The work done, W, comes from the difference between these two heat flows, or net heat input. W is equal to QH minus QC. Since heat only spontaneously flows from a high temperature reservoir to a low temperature reservoir, a heat engine needs to work between two thermal reservoirs in which there is a temperature difference between them. The efficiency of a heat engine is given by the general definition of efficiency being equal to what you want divided by what you pay. In the context of a heat engine, the net mechanical work being done divided by heat input, QH. And from the study of Carnot engine, we know that this efficiency is greater for greater temperature difference between thermal reservoirs. So the efficiency is limited by the available temperatures of thermal reservoirs, how low the cold reservoir is, and how high the hot reservoir can get. Yeah, that's probably longer than most answers I'm expecting it to be. Let me move on to question number 2. The second video in particular illustrates how efficiency of a heat engine changes with the temperature difference between two thermal reservoirs. Watch the first video for explanations of these terms. In particular, consider and answer this question. The alcohol lamp at the hot reservoir provides a constant input heat flow to the Stirling engine. Why is the heat engine not able to start for the first minute or so of operation? Once the heat flow stops, lamp is blown out, the engine comes to a stop. Why does it take far less time to restart the engine for the second time? Yeah, I think I mentioned that. Make sure your answer to this question relates to the heat engine efficiency somehow. And this is the model answer. Number 2. Why is the heat engine not able to start in the second video for a while with the second try taking far less time? Wow, that is long description. The key here is efficiency. From the study of Carnot cycles, we know that a necessary condition for an efficient operation of a heat engine is the temperature difference between the two thermal reservoirs. Even though the power input from the alcohol lamp remains constant through the run, at the beginning, where the hot reservoir is barely hotter than the cold reservoir, the efficiency of the engine is so low that the work produced cannot overcome friction. When the hot reservoir gets hot enough, the efficiency of the Stirling engine becomes good enough to produce enough work to overcome frictional forces. And it is quicker to start the engine a second time because the hot reservoir is already close to hot enough, so it takes less time to reach the operating temperature. This, by the way, is why, as a prime mover, heat engine is not so good. I mean, it's so finicky, it needs right operating temperatures and all that. We'll talk about the motor soon, and electric motor is a much better prime mover because it's so much simpler. All right, let's look at heat pump. This video, I think I have actually played it for one of the lecture videos before, so I won't do this. You've seen this as part of a lecture video. And let's see. Oh yeah, and I mentioned the thing about the boiling water until it freezes. This is the kind of the thing You can find on YouTube. So let me play this. It's from about 2-minute 20-second mark till about 6-minute 50-second mark. Again, I won't play the whole thing. I'll just kind of skip around to show you a gist of what the video covers. All right, this is from the channel Cody's Lab. I haven't seen videos at the channel in a while, but let me skip ahead to 220 mark. So that's where you will see everything set up, and he's gonna close the vacuum chamber and start to pump things out. I think the white stone looking thing is the desiccant. Keeps the chamber nice and dry. So I'm gonna just skip ahead to the pumping part. Yeah, dissolved oxygen. And then when it starts to boil, you will see a more kind of vigorous boiling. Yeah, that's boiling, and he's gonna show you the temperature of the water, I think. Yeah, is it 9 degrees? I can't quite read. In actually, with the water in there, it takes more time to kind of vacuum out the chamber because the water boiling, that's a kind of new source of gas. Thermometer starter. But he has a much better pump setup than I do, so he's gonna be able to basically keep boiling it until it freezes. So let me skip ahead to that part. Let's see, and here's the chamber thing. Yeah, and it had a frozen top, and I think once the layer froze, then the rest of the water didn't wasn't able to boil. Yeah. So you can find the video yourself. But yeah, it's quite old video. Because I think it was already old when I was setting up these assignments. So let me close that. And the next video, it's from Danfoss Cool, is just showing the operation of the refrigerator. It's got compressor in there. So let me just again play it and just skip through it with the captions enabled. So I'm gonna make sure I enable the captions, and I'll just skip ahead. So I'll pause around the part that shows essential elements of refrigerator. So that's the kind of the radiator radiating heat into the environment, and inside there's a similar looking thing. It's called the evaporator, and it's colder than the colder inside, and the condenser, that's what I was calling radiator. This is hotter than the room temperature, and it releases heat into the room. And at some point they will describe what the pump does, compressor. So that's the compressor. So the heat flow, I'm trying to think through. I think it flows from so I guess yeah, so it leaves the compressor. So the direction of the flow is leaves the compressor, enters here. It's a hot gas, and through this condenser, it's radiating heat into the environment, cooling down, and by the time it gets to this end here, it's condensing, and then as it goes through this kind of needle sized opening, it gets evaporated here, and through this evaporation, this refrigerant further cools down. So within here, it's quite cold, colder than the colder inside of the refrigerator. So this is absorbing heat, kind of reaching whatever the end limit of the the, the refrigerator temperature is. And then I think I guess I moved past that, and this returns to the compressor, this return line. So this is where the refrigerant is returning. By the time it's returning, it's basically at the temperature of the high end of the refrigerator, and then as the compressor does work, that work increases the temperature of the refrigerant. So it exits here again relatively hot, and then it goes through condenser and so on. So that's the kind of the setup here, and again you can find the video and watch it for full explanation. Yeah, and then there's a thermostat and all that, and this is the kind of the schematic representation. The compressor is like a heat engine being run backward, where you put in work rather than getting work out of a heat flow, and through that work you put in, you are able to make a heat flow basically in opposite direction, from cold to hot. So yeah, that's the setup. All right, so I think that's all the videos. Let me read questions 3 and 4. Question 3. The idea that evaporation is a cooling process is a familiar and intuitive one. What sounds counterintuitive at first is this claim: boiling is a cooling process. But hopefully the first 2 videos above have convinced you of the veracity of this claim. Explain how boiling is a cooling process. Make sure your explanation refers to latent heat or latent heat of vaporization, to be specific. What is the key difference between evaporation and boiling? And here's the model answer number 3. How is boiling a cooling process? As the liquid turns into gas, this process requires energy. You can explain it as any one or more of. 1, because it involves breaking of bonds, the bonds involved in forming liquid or solid. 2, because the potential energy between molecules must increase. And 3, because of latent heat, which is what we measure to express this. In the absence of additional energy source, for example, applied heat, this required energy comes from the thermal energy of water itself, causing it to cool down as it boils. The difference between evaporation and boiling is simple. In boiling, water turns into water vapor throughout the entire volume of the water, while in evaporation, water turns into water vapor only at the surface of the water. Boiling happens when vapor pressure of the water is equal to the ambient pressure. This is a Wikipedia link to vapor pressure. Otherwise, evaporation and boiling are the same. They both require energy input, latent heat of vaporization, so they are both cooling processes. Okay, let's look at number 4. In the last video above, the inner workings of a refrigerator is explained, including the cycle in which the refrigerant fluid absorbs heat from the colder inside of a refrigerator and releases heat into the hotter outside. According to the second law of thermodynamics, work must be done to cause this heat flow from cold to hot instead of the usual spontaneous hot to cold. Which part of the refrigerator provides this work? Explain how this part does work. So the model answer number 4. Which part of the refrigerator is responsible for non-spontaneous flow of heat? The part of the refrigerator that does work is the compressor. That is all the answer that is needed for an answer to be correct. But here is a bit more extra explanation. The compressor takes the refrigerant gas coming out of the refrigerator, cool gas phase, low pressure, and compresses it into the radiator slash condenser part of the system, turning the refrigerant hot, still in gas phase, and at high pressure. With this work done on it, refrigerant can be, one, when inside the refrigerator, colder than the cold inside to absorb heat, and two, when outside the refrigerator, hotter than the warm outside to release heat, so that each time the actual heat transfer happens spontaneously in a way consistent with the second law of thermodynamics. And when you look at the process as a whole, you point at the work done by the compressor to say this is what pumped the heat opposite to the spontaneous direction. Alright, let's move on to the next chapter. That's chapter 9, essay assignment. And then let me load the peer review here. Let me see how long the videos are. Might not play them all. Yeah, the bouncing tab one, I think I showed that in the lecture video. I mean, if you want to search it, you can search it. Oh, I guess that's on my other channel. But I'm pretty sure I showed this, the kind of the tab bouncing between the two charged spheres. So there's that. This actually has a bit of a longer demo than what I've shown. And this home electrical system safety, let me not play it. I see that I'm a little bit running low on time. So I'll just show you enough so that you can find the video if you want. It's a home electrical system safety by Electrical Safety Foundation International. And this is sort of what it is. There's the whole bunch of things, and I'll just address it in the model answer. So the questions. Question number 1. In the first video, the one with the aluminum tab bouncing back and forth, explain what is going on, assuming Van de Graaff generator is charged positively and the grounded sphere is charged negatively. Explain why the aluminum tab is attracted to one sphere, but as soon as it touches the sphere, it is immediately repelled away to the other sphere, repeating the process for a long time. And here's the model answer for question number 1. Explain what is going on with the aluminum tab and the VDG generator. Two important things. One, the sphere and the aluminum tab are conductors, and electric charges readily move into or out of or around the conductors. And two, like charges repel and opposite charges attract. So when the aluminum tab touches one sphere, it gains the charge of the sphere, being pushed out of the sphere onto the aluminum tab while it is in contact. And because like charges repel, it becomes repelled from the sphere it just touched, being bounced to the other sphere. The process continues until both the spheres are discharged from the aluminum tab, carrying the charges back and forth, almost like a shuttle. Note, there's a small detail about how the tab initially gets attracted to one sphere. This is through polarization, but we're not going to worry about that for now. So to kind of jumpstart the process, the tab gets polarized, positive one side, negative on the other side, and that allows initial attraction. Okay, question number 2. The second video, the one made by ESFI, illustrates some of the safety features built into your home electrical wiring. List 3 of the safety features, name them, and explain how each safety feature works. What is their purpose and when applicable? What is the physical mechanism for their function? And here's my model answer. I think I mentioned all of them that's in the video. Explain home electrical wiring safety features. For your convenience, all the safety features mentioned in the video are listed below. The student answers are required to list and explain 3 of these features. Fuses or circuit breakers in service panel. protects the wires in the circuit from overheating by stopping the current from flowing if it exceeds the safe levels, either from overloaded circuit or other electrical hazards, faulty appliance connected, and so on. And within the circuit breakers, there's something called arc fault circuit interrupters, a type of advanced circuit breaker which can detect arcing condition, a major cause of electrical fires. Grounded electrical systems protects shocks or electrocution by providing a path of less resistance for the current to flow. In case a fault in the appliance causes the exposed cover to become electrified. And grounded outlets, the third round hole is grounded, providing a way for compatible appliances to be grounded. And there are outlet adapters that connect those grounding, connect to nothing, which can work for the time being, but it's less safe. Ground fault circuit interrupters. These are usually installed at the outlet level, like in a bathroom outlet. Protects from shocks or electrocution by stopping the flow of electrical current if the flow of electricity is disrupted. Usually used in places exposed to water, bathroom or kitchen, where the water may create a dangerous short condition. Tamper-resistant receptacles. Protects from shocks or electrocution with a spring-loaded shutter system which prevents children from inserting objects into the power outlet slot. Polarized outlets. Two vertical slots of different sizes makes it difficult to insert a plug the wrong way. It has to do with which end of the plug is the hot plug that has a large 110, 220 volts, and the other is the cold or the what's supposed to be close to 0 volts. Okay, so that's electricity. Let's look at magnetism. So we have essay assignment. Let me pull this peer grading thing to the side. And I think, I think I have the eddy current demos. Yeah. These are, so you've seen the demos that I recorded. These are kind of fun demos that you can find on YouTube. So this is one with a really large neodymium magnet. So let me just show you for a couple of these illustrations. When he drops the magnet, you will see it. Yeah, it's almost surreal. He's gonna drop it and watch. Oh wait, yeah, it's like coming gently to a stop. And that's because the eddy current is slowing down the magnet. Yeah, pretty cool. If you want to hear his explanation, you can go watch it. And this is, I'm not sure if I remember details of this video, but let me just briefly play it. Again, I'll kind of skip ahead. It's about magnetic braking and eddy current, which again, I had my own demos. Let's look. Maybe this is exactly same as my demo. Except I don't think I recorded a top-down view. Because I don't know. Yeah, so this kind of matches the explanation that I've given in the lecture video that you have seen. Except this is more physically correct. With a slit, that is the conducting loop, and those will kind of dissipate away mechanical energy. And I don't think I have this demo. Oh yeah, that this will kind of swing between these magnets, and I think they might have I guess these are electromagnets. They might have ones with like a comb-like thing built in that will yeah. So these won't be stopped as easily because those perforations stop the current from flowing. Yeah, I learned recently the triple beam balance has a metal object like this near a magnet to kind of damp out the oscillations. This is a way to damp out motion without there being any permanent like pull one way or another. So, so those are the videos. Let me read through the questions. So here's question 1. As you see in the videos, when a magnet moves relative to a conducting non-magnetic material such as copper, some force slows down the magnet, and this is attributed to eddy current. Describe in your own words what this eddy current is, how it is caused, and how this eddy current affects the magnet which caused it. This is a kind of an open-ended question, so this model answer is just one example. It describe in your own words what this eddy current is. Eddy current is excellently described in the second video, so a summary of the description from the second video is a good answer. Here's a model answer. Eddy current is a current that is generated as a result of Faraday's law and properties of conductor. When magnetic field in a conductor changes, for example, because a magnet nearby is moving, according to Faraday's law, this induces an electric field, which results in an induced voltage. This induced voltage in a conductor causes a current to flow in small and large loops. Lenz's law says that the direction of these current loops are oriented so that the magnetic field due to these induced currents oppose the original change in magnetic field. And while detailed analysis is a bit complicated, the overall result is that there is an induced magnetic field that opposes the motion of the magnet. So eddy current induced by a moving magnet slows down the magnet. This effect is used for mechanical systems such as magnetic braking. Question number 2. As you see the demonstrations of eddy current, you should realize that these demonstrations involve non-conservation of mechanical energy. You see 1. A large magnet slowing down to a stop at the end of a short stop before hitting the copper plate, which means loss of kinetic energy. Number 2. A magnet moving downward at a constant velocity, loss of potential energy. Or 3. A pendulum slowing down to a stop, loss of total mechanical energy. These mechanical energies are likely being lost to heat. Explain the mechanism by which this loss happens. Hint. What happens when a current flows in a material with non-zero resistance? So here's the model answer. Number 2. Explain the mechanisms of mechanical energy loss in physical demos involving eddy current. This question ties in with question 1. In short, the mechanism by which mechanical energy and the electrical energy represented in the flowing current is turned into heat energy is the heating that happens in the current carrying resistor, sometimes called Joule heating. As the induced current flows through the conductor, the resistance of the conductor causes a dissipation of the energy. According to the formula, power is equal to current squared times resistance. In addition, the direction of a magnetic field given by Lenz's law will always act to slow down the moving magnet, acting as a friction force does. Okay, so that's magnetism. Let's look at the last of the essay assignments on light. Let me load the peer grading item here, and let me play the essay assignment. Oh, I think I remember. Some of the videos I'm using, I think it comes from there was a YouTuber called King of Random. He passed away some years ago in an accident. I'll just mention that. So I think there's quite a bit of videos, so I won't really have time to play them all. I'll just show you the videos so that you can find them yourself. Supersonic Flights, Sonic Booms by AV Web. You can find it yourself. And here's a picture of supersonic waves. There's a photography technique that shows those tiny density changes. Picture of a supersonic shock wave, uploaded by Don Humphrey. So there's a imaging technique. I don't know if that's showing here. Maybe it's not showing here. Anyways, you can find and look at it. And there's a video about Cherenkov radiation uploaded by SciShow Space. It's the radiation produced by fast-moving electrically charged particle. It's sort of like a shock wave, except it's a light shock wave. So you can watch the whole video. And an example of Cherenkov radiation can be seen in what's called nuclear reactor pulse. Yeah, I think they're gonna. Actually, this is pretty short, so let me play it with the sound on. So the pulse is turning on the nuclear reactor. I imagine they did it with some control rods and whatnot. And when the nuclear reactor turns on, starting nuclear reactions, it emits, I guess, beta rays among other things. And there's a it's in a water bath. The water both acts as a coolant and moderator. And as those fast-moving beta rays, electrons are moving through the water, it's emitting that glow. That's the Cherenkov radiation, kind of bluish-looking light. And yeah, so that's an example of Cherenkov radiation. And finally, yeah, these two are, I think, the videos by King of Random. Yeah, they, I guess, rebranded the video TKOR. And the guy who appears in this video, he's the I used to use some of his videos, including this one. He has some pretty cool demos. So this is him using something called a Fresnel lens that he salvaged from an old flat screen TV, and he's using this to as a kind of solar power thing. Yeah, he's burning stuff there. King of Random. And I think this is his second video doing the same thing. So it's the other video where he's burning more stuff with it. Yeah, this can be pretty dangerous. It's like I think he might even melt some metal with it in some of the demos. I think, is that onion? No, that's egg. I think maybe, not sure. But anyways, if you want, you can go watch it yourself. Yeah, this is already a long video, so let me. I'll read the questions and read the model answer. Question number 1: what condition is necessary for a shock wave to be created? How are sonic booms, a kind of sound wave, and Cherenkov radiations, a kind of light wave, similar? How are they different? Some part of the answer is already in the question, but let me read the model answer. What condition is necessary for a shock wave? The key necessary condition is that the source of the wave must be moving at a speed faster than the speed of wave. Under this condition, the wavefronts of wavelets produced at different times as the source moves build up along a conical surface. It looks like a line in cross-section, which forms the shock wave. An object, like a supersonic jet, generates a sonic boom when it travels faster than about 340 meters per second, speed of sound in air. A shock wave of light, Cherenkov radiation, is generated when a fast-moving charged particle, such as an electron, moves through a transparent material, like water. If the electron in water is moving faster than speed of light in water, then it generates Cherenkov radiation, seen as the blue glow in the nuclear reactor pulse video. These two types of waves are similar in that they are both shock waves formed under the condition described above, They are different in what type of wave they are and how fast they travel. Sonic booms are sound waves traveling at about 340 meters per second in air. Cherenkov radiations are light waves traveling in water at about 225, I guess that's a million meters per second. Question number 2. Explain how light shock waves are created if light is the fastest moving thing in the universe. As an example, describe how the blue glow in the nuclear reactor pulse is created. Seems a little bit duplicative, but let me read it. How are light shock waves created? The first thing to explain is that the speed of light in vacuum is the fastest anything can move in universe. Light moves at a speed of about 300 million meters per second, or 3 times 10 to the 8 meters per second. But when light enters a transparent medium, such as water or glass, it slows down. How much light slows down is expressed by index of refraction. In water, light moves at about 3/4 of its speed in vacuum. So index of refraction of water is 1 divided by 3/4, or about 1.33. In glass, light moves at about 2/3 of its speed in vacuum. So index of refraction of glass is about 1/2/3, or about 1.5. So suppose you have an electron that moves at 95% of speed of light in vacuum. When it enters water, it is now moving faster than speed of light in water, about 75% of speed of light in vacuum. So the conditions for generating shock wave is met, and the shock wave created is the Cherenkov radiation seen in the video. So Cherenkov radiation cannot be generated in vacuum, or with the electrons that are moving slower than the speed of light in the medium. One additional note, the shock wave does not have a specific frequency or wavelength. If you ever heard a sonic boom, you wouldn't hear a specific pitch either. It is a superposition, that is combination of wide range of wavelengths. Our color vision perceives the combination of all the wavelengths in the Cherenkov radiation as light blue color, but it'll be a whole continuous spectrum. Okay, question number 3. List of the optical elements, lenses, mirrors, and anything that is designed to guide and shape light rays found in the old large screen TV, as shown on the 5th video above. And here's the model answer. List of the optical elements. Following are the optical elements found in the TV. Cathode ray tubes, producing 3 colors, red, green, and blue. Lens casing containing about 5 different optical lenses, including a glass focusing lens, flat projection mirror, and TV screen with 3 layers. Plexiglass, just a flat, transparent, glassy looking plastic, sometimes called acrylic. Vertical lined plastic, and Fresnel lens. The most important elements are cathode ray tubes. This is where the TV light comes from, focusing lens, and the Fresnel lens, being responsible for how you can see the image on the TV. Okay, last and final question, question number 4. The centerpiece of the optical elements pulled off the large screen TV is a special type of lens called Fresnel lens. It's spelled like a Fresnel lens, but I think this S is silent. Fresnel lens, because of its large area. A Fresnel lens can focus a large amount of solar power into a small area, as demonstrated in the last video. Describe how a Fresnel lens is made and what other applications exist. You may find this Wikipedia page on Fresnel lens helpful. And I think I have also shown demos of image formation using small Fresnel lens I have in lab. So you have seen a couple different Fresnel lenses. So describe construction of a Fresnel lens and its applications. Fresnel lens is constructed as a series of concentric rings of surfaces angled to focus light. The way these surfaces are angled is as if you took a regular lens and keep only the surfaces, getting rid of bulk of the material between the two surfaces. The illustration of the cross-section of a Fresnel lens, number 1, and of a regular converging lens, number 2, on the right from Wikipedia page, shows the result. The main advantage of Fresnel lens is the focusing power you can obtain for a large lens with a much thinner material. You have seen in the video that Fresnel lens was used for a big screen TV. Fresnel lenses are also used for construction of lighthouses and in different parts of automobiles, a headlight for focusing the light from lamp, and in some large vehicles for reduction of blind spot by building a Fresnel lens into the rear window. You can also find the small Fresnel lenses being sold as lightweight handheld magnifying glass. Solar power hobbyists also find the use for Fresnel lens. The video you have seen would be one less practical extreme example of this application. Okay, so that's the last of the essay questions. Again, you might see in some of the timed assessment essay questions, some of the questions similar to these because those questions are written assuming that you have done these assignments, which now you're not, but that's the reason I'm doing this video and reading the questions and answers out loud. And again, if you want to watch those videos, you can find them on YouTube. They're still all up. At some point, some of them might be taken down in some future, but they're still up for now. Thank you, and I'll see you next time. Bye. So this is a lecture I've wanted to do for a while, telling the story of light. And I thought this intermission between Unit 3 covering classical physics and Unit 4 going into modern physics would be a perfect time for this extended story about light, its role in modern physics. So let me do this lecture in 3 parts. I'll record this and then I'll divide it up into roughly 3 parts, just telling the story of light at different phases of how much we understood about light. By the way, these slides are generated using Notebook LM. I wrote out an outline of what I wanted to talk about, and this is the AI generated slides from that outline. Some of the wordings are not exactly, the way I would have worded it, like humanity's quest to decode the universe from the dawn of biology to the quantum realm. I'm not sure if I would have said that, but it's correct enough. If I say anything that's actually incorrect, then I'll correct it as we go. So, light. Both the word and the concept itself, I think it's something that has almost a primordial importance, or it's the kind of idea that I don't think there was ever a time in the written history or even way back into prehistoric times where the concept of light didn't play a role. This is from Book of Genesis, the first 3 verses. In the beginning, God created the heavens and the earth. Now the earth was formless and empty. Darkness was over the surface of the deep, and the Spirit of God was hovering over the waters. And God said, "Let there be light," and there was light. In fact, that's the motto of my alma mater, Fiat Lux, or the Latin for "Let there be light." And if you look at any myths or philosophy from the earliest times, you will see the concept of light playing a role. We talk about light versus darkness, And I guess I'm thinking of more modern sci-fi stories about forces of light. It means, forces of good. It becomes an almost metaphysical thing in itself. But when we talk about light in this physics class, we are talking about the physical phenomenon of light. And it influences so much of our thinking. And as a scientific example, so in biology, there's something called convergent evolution. This is referring to when you see organs evolving, popping up in different species, but that don't have obvious common origin. Like think of wings of an insect versus wings of a bird. They are organs that serve the same purpose, flight, but they are so obviously different that they don't have a common origin. And eye is another organ that you will find examples of convergent evolution in. I'm not a biologist, so I can't give you examples, but I know of insect eyes, and those eyes look very different from our eyes, and they serve the same function within the organism of being able to perceive what we call light. And I think, again, I'm not a biologist, but I think it makes sense. We live in an environment that just bathe in what we call light. It carries us to so much information about our surrounding at much faster speed than we could gather them if we are feeling by touch. And I think maybe it's because of the way our eyes developed. We can usually get more detailed information through our sight than we could by hearing. I have heard of blind people who use like clicking sound to try to get a sense of the place they are in. But we human beings at least are not. We haven't developed a general ability for echolocation, and way more species on Earth and in the seas have eyesight than there are species that have developed ability for echolocation. And that shows just the importance of light. If you read science fiction, there are some, sci-fi writers who imagine, species on a different planet developing either without sight. I think that's one of the examples in the upcoming, or was it already released? Upcoming movie based on the novel Project Hail Mary. The other aliens, sorry, spoiler alert, they come from a world where there is much light, so they didn't develop eyes like us. And I remember another sci-fi short story about this is about a world that orbits multi-star system, and this is more about the people on that world never having seen a night sky, and we owe a lot of our scientific developments to information that we could gather from light observing our night skies in the early times. Now, just one more thing about our some ideas about sight. So this is the slide that Notebook LM generated based on kind of section of Feynman lectures that I coded in my outline. But let me actually just go to that section and read it out loud. This is from first volume of Feynman lectures. I think chapter 26, section 1. Let me browse to that. So it's in volume 1. Chapter 26, and section 1 is called light, and it's this section that I had in mind when Feynman relates some of the early theories about vision, and it's this section. Yeah. So let me read this paragraph. So first, light is, of course, familiar to everybody, and has been familiar since time immemorial, as I was saying. Now, one problem is, by what process do we see light? There have been many theories, but it finally settled down to one, which is that there is something which enters the eye, which bounces off objects into the eye. We have heard that idea so long that we accept it, and it is almost impossible for us to realize that very intelligent men have proposed contrary theories, that something comes out of the eye and feels for the object. For example, almost like Superman's eye beams. Some other important observations are that as light goes from one place to another, it goes in straight lines if there is nothing in the way, and that the rays do not seem to interfere with one another. And we talked about wave interference and superposition principle. That is, light is crisscrossing in all directions in the room. But the light that is passing across our line of vision does not affect the light that comes to us from some object. This was once a most powerful argument against the corpuscular theory. It was used by, can't pronounce this name right, Huygens. If light were like a lot of arrows shooting along, how could other arrows go through them so easily? Such philosophical arguments are not of much weight. One could always say that light is made up of arrows which go through each other. It's the property of light particles not to collide with each other. And we'll get to that in the later parts of this lecture. All right, back to the lecture slides. And I can imagine wrapping up these pre-scientific ideas about light. I can imagine even in prehistoric times, someone making this observation. I'm inspired by. So if you read ancient texts like the Peloponnesian War by Thucydides, you can see that ancient people had what we might call scientific attitudes towards the natural world. In fact, there are a couple incidents of solar eclipse that Thucydides describes, and he observes that these kind of solar eclipse seems to happen only during new moon. And I don't know if he actually mentioned the possibility of eclipse being moon covering the sun, but ancient people, this is from like, what is it, 400, 500 BC, and humans back then were just as smart, intelligent as humans we are now. And I think enough people had the attitudes that today we would call scientific. And the example I'm thinking of regarding light is example of lightning. That's one phenomenon, lightning and thunder. That one single event, lightning striking something, and that would result in actually two different waves, sound wave and light wave. And I can imagine an ancient, intelligent caveman in a thunderstorm, looking at the lightning and maybe being a little bit scared, observing that when he sees a flash of light, that he doesn't hear the thunder immediately. And they will always appear to be connected, like when enough that when he sees the bright light in the sky during the thunderstorm, he will be able to expect, oh, there's a thunder coming. And someone who's observing this well enough, maybe a little bit harder for cavemen. I'm thinking of modern houses with the windows where we are protected from elements, all that. But someone can observe that some relationship between how long it takes for you to hear the thunder and maybe the loudness of it. Some indicator of how close was the lightning strike versus how far away. And so in the context of this class, we give some rule, you count of the seconds and you multiply that by, 340 meters per second. That gives you the distance in meters to how far away the lightning strike was. And in observations like that, we today can see that this is an example of the different travel speed of light and sound. Light, it almost seems instantaneous, and sound, you can hear in comparing with what you see that there's a delay in the sound. So we are now about to move on to talking about scientific theories about light. Let me do that in the next part. Okay, we are back, and I was talking about how I was imagining someone observing a lightning strike and realizing that there's a delay of time in when you hear thunder after a lightning strike, and that might lead someone to imagine that sound is traveling slower than light. And once you observe that, then you might also think, does the light take some time to travel, like sound? And some people in the Renaissance period did think about that. I think Galileo was actually one of the people who thought there might be a delay in the transmission of light and tried to measure it. And back then, just with how fast the light is and limited kind of temporal resolution of their measurement methods, they had to conclude, at least as far as they can measure, there's no delay time with the light measurement. But not too long after, people were actually able to see the delay time of light. It just takes an astronomical context because you need astronomical distance for the delay time to be measurable. Just as a kind of numerical reference, it takes from where we are on Earth to travel to the moon by light, it takes about 1 second. If you ever hear one of those Apollo transmissions, there will be a couple seconds delay between the Earth station saying something and the astronauts responding. And it's not just the astronauts kind of thinking about their response. About 2 seconds of the delay is the round trip transmission of the radio waves. So back in the Renaissance times, or post-Renaissance, I guess, this might be beginning to become modern. So I think we briefly mentioned the Galilean moons. This is in the discussion of geocentrism and heliocentrism. And Galileo was observing planets with his telescope. And as he was observing Jupiter, he saw the moons going around Jupiter. I mean, from our perspective, the Jupiter looks like this and the moon looks like it's moving in a straight line back and forth. But with some imagination, you can imagine you are looking at a kind of a side view of something that's orbiting around, like our moon orbits around Earth. The 4 biggest moons of Jupiter are what we today call Galilean moons because Galileo discovered them. Oh, I don't know if I remember all of them. There's Ganymede, Europa, Callisto, and Io. And of these, Io has the shortest period, I think, on the order of a few days. And so Galileo discovered them, and by the, I guess, the late 1600s, they were observed for long enough, characterized well enough that people knew the exact orbital period. I had to look it up, 1.77 days, and basically knew when they should expect to see Io, as it orbits around Jupiter. And this is also the time, time of great exploration, a lot of naval explorations, and for reasons I won't go into, sailing by ship is one of the driving forces for more accurate timekeeping devices because it's necessary for navigating the oceans when you don't have any landmarks to see. And around this time is when the Greenwich Observatory is established. And even today, when we talk about Greenwich Mean Time, which is the time zone that all the other time zones are established relative to, that's after the location of the observatory in Greenwich, England. Anyways, all of this timing stuff, as astronomers are observing Io, they realized that sometimes the transit of Io across Jupiter happens too late or maybe too early. So there's a time at which they would expect this event to take place based on years of measurement and just knowledge of the orbit of Io. But when Jupiter is farther away from Earth, they could figure this out both based on the brightness and just the relative position of Earth and Jupiter relative to the Sun. When Jupiter is farther away from Earth, they would see that, oh, this transit of Io, it's happening later than we were expecting it to. And when Jupiter is closer, then I don't know the exact story, if it would be kind of at the same time they expected it to, or maybe earlier than they were expecting it to. And all of this boils down to the travel time of light from Jupiter to Earth. From Earth to Sun is about 8 minutes, and Jupiter is farther away. So between Jupiter and Earth, depending on where you are on the respective orbits, either it would take, I don't know, 30 minutes or only a few minutes. And this observation, the orbital timing of Jupiter's moon Io, and how it appears to shift depending on the relative positions of Earth and Jupiter, they could estimate the speed of light. And this early measurement, it was off by some like 20-30%, but this is the first indication that light doesn't travel instantaneously between places. It has some finite travel time. And I think this measurement was made by Huygens, the guy that Feynman mentioned. Now, this is the great classical period for physics. This is the time of Newton, time of a bunch of people, and they had a big debate about nature of light. And I don't think we talked about this specifically. So there's the corpuscular theory of light. This is Newton's theory. He's the main person to propose this. And when I was looking up Wikipedia preparing for this lecture, I saw Robert Boyle. I think he is known for his work in chemistry. Boyle's law is one of the gas laws, I think. Robert Boyle was one of the supporters. And I put the name of Poisson in for one of the illustrations. And for this corpuscular theory, the main claim will be light is made up of stream of particles, fast moving, discrete physical arrows streaming through space. That seems to match with how we usually observe light as a ray of beam. We still use the construct of ray when we are doing some optics stuff. You saw that in the last chapter. And if I were a proponent of the corpuscular theory, and I were making argument for why light must be particles, I would use Occam's razor, that all things being equal, two theories having similar level of predictive power, seemingly, the theory that I would trust in more, or I would gravitate towards too, would be the simpler one. Given all the different explanations of about similar credibility, what I would believe is the simpler one. The corpuscular theory is almost certainly simpler, and there's nice analogies we can use with the atomic theory and the particles that make up the elements, and light is our particle for the I guess light was never a classical element, but it's the particle for whatever kind of elemental thing we would associate with the light. And also it explains why light travels in perfectly straight lines. It's like a ball moving straight, unaffected by gravity, or given how fast it's moving, minimally affected by gravity. And that would be the position of the people who believe that light is particle. And this debate went for some time. The wave theory, the people who are in favor of wave theory, they certainly didn't have the stature of Newton, but there were people who believe in the wave theory. And unlike earlier scientific debates like the geocentrism and heliocentrism, no one was being burned at the stake. So Christian Huygens is one of the early proponent of the wave theory. In fact, we talk about something called the wavelets. That's a Huygens wavelets. So I think in the lectures you've seen, I make reference to using those wavelets to drive the law of reflection and law of refraction. I mentioned it, but I never actually do it. In Physics 4C, I do actually do it. And let me mention the names of Thomas Young and Augustine John Fresnel. I think you heard the name Fresnel before with the Fresnel lens. And with the wave theory of light, basically you are treating light as a wave. And by this point, people have seen waves in other places in classical mechanics. Waves on a string, waves on a water surface. I don't remember if they understood the sound as waves too. They probably did. So the argument here would be light is like that. It's something oscillating in space that's traveling like many other waves you have seen. And I guess according to Feynman, the main argument that Huygens made for that was how light goes through each other. That seems like what we see in waves with the superposition principle. And in the 1600s and the 1700s, time of Newton, this debate went on. And for the most of the time, Newton, again, being the most prominent physicist among them, Newton held sway. Corpuscular theory is what most people believed in. Now, there's something we call Young's double slit experiment. That's the first, almost conclusive evidence that light is wave. Because Thomas Young did this experiment with so this is back then when they didn't have lasers, so they had to set up these optical experiments very carefully. So he first set up a single slit through which some light would go through, and then a double slit after that. Then the light from single slit goes through the double slit, and then there's a screen where the light kind of intensities are shown. And when you look at that, you see an alternating pattern of the bright and dark fringes. And bright fringes, I don't know how conclusive that portion is, but the dark fringe is the kind that you would only get through wave interference, the destructive wave interference. If a light were particles, then two baseballs don't cancel each other out. You could have two baseballs coming together in one spot, giving you two baseballs, but you wouldn't somehow have them cancel out to give you zero baseballs. But with the waves, you can have them interfere in such a way that in a place where one wave goes up, the other wave can be going down. So when you add them up, superposition, they add up to give you zero at that spot. So this destructive interference that you can see, that would be almost conclusive evidence that this can only be produced by wave. Now the debate would go on for some time. I don't think everyone was immediately convinced by Young's double slit experiment. And in fact, there was a competition. I want to say 1817 maybe. There was a competition in 1818. There was a challenge to about the nature of light. What is it, and how do you demonstrate that the light is the thing that you say it is? And this is the competition to which Fresnel, the name didn't make here. It's the Augustin John Fresnel submitted an entry to. He proposed a wave theory of light that he detailed in his submission to this competition. And Poisson, Simeon, Denis, these are all French names and I don't know how to pronounce them. Poisson was one of the judges. And so he was trying to poke holes in the theory, to try to show why it can be true. So he was attempting to destroy the wave theory by pointing out an absurd consequence. So imagine this is a shadow being cast by a perfectly circular disk of material. Then what Poisson pointed out was, well, with that idea about wave interference, so all these edges, they've kind of become like a wave source for the light that's bending around the edge of the disk. And what he was arguing was each of these points being at the same distance to the center, not the center of the disk, but center of the shadow. So you have to kind of imagine there's a perspective effect collapsing it. All these being the same distance to the center. At the center, you would get some kind of constructive interference. And what he was predicting that he thought was just absurd prediction that shows why wave theory cannot possibly be right, is this spot that we would call Poisson spot. It's in the center of the circular disk shadow that looks bright. Like, why are you seeing light in the middle of a shadow? So that, on the face of it, sounds absurd. Now, this picture is a little bit exaggerated, so let me show you a more faithful picture of what Poisson spot looks like. So this is the Poisson spot, or what Wikipedia calls Arago spot. So in this shadow of a disk, so around the edges, you get a knife edge diffraction. That's what these ripples are about. And you have the bulk of the shadow, and in the very middle is where you see a very kind of a slightly brighter spot in the very center compared to the rest. So that is Poisson spot. Again, proposed as an absurd prediction of the wave theory of light. Now, someone, Arago, he was another judge at the same competition, Dominique Francois Jean Arago, I don't know French names. He was a proponent of wave theory, and he thought, hey, the prediction seems sound, to following the theory. And this is an experiment that's never been done before. Why don't we do the experiment? See what happens. So he meticulously performed a physical experiment to test this prediction. And he saw that spot that you saw just a while back. Now again, it doesn't look bright like this. That's more of a what you would see if your disk had a literal hole in it. Not like that, but more like this. If you look carefully, there's a spot in the middle. So even though it was proposed by Poisson as a kind of absurd prediction of wave theory, it turns out to be the correct prediction that actually experimentally happens. So the bright spot appeared exactly as predicted. The constructive interference in this geometry was proven real, and the scientific establishment universally accepted that light is a wave. I mean, there are probably people who never believed it to their death, probably. But, this is a kind of example of how we want scientific process to go, Someone has a theory that's, interesting, says something that we wouldn't simply guess, and someone makes a prediction following the paradigms of that theory, and that prediction, sometimes predictable or sometimes absurd, and someone does the experiment, and the experiment either confirms the theoretical prediction, or maybe the experiment doesn't confirm it. Then you have to iterate. You have to maybe modify your theory. Maybe you made a mistake in the experiment. In fact, doing this experiment before lasers would have been very challenging. You had to have a really good point source of light. And today, this is a lot easier to do. You just shine a laser beam to I think like a bearing balls. Then in the shadow of the bearing ball, you would see this Poisson spot. But before lasers, this kind of light experiment would have taken a lot of care to set up correctly. You mess it up, then you wouldn't see this spot, but not because theory is wrong, but because experiment was done carelessly. Now, even though this wave theory of light was accepted, people still didn't know wave of what. Like, what is the thing that's doing the oscillating? Because light isn't like any other wave. Sound waves, it doesn't go through a vacuum. You have a sound source, put it in a vacuum chamber, vacuum it out, you don't hear it anymore. But light, we know we can see it through a vacuum. So whatever mechanism vacuum chamber works on air, it doesn't work on whatever is the medium for light. So even though people accepted wave theory of light, for many years we didn't know what it was that was doing the waving in light. This is this is where we ended the last unit in. This is where Maxwell comes in with his theory of unified electricity and magnetism. James Clerk Maxwell, he was a theoretical physicist, and theoretically, thinking through physical scenarios, he spotted a missing term in what we call Ampere's law that describes how magnetic fields are produced by current, electric current. And in order to reconcile the contradictions there, he had to introduce a new term that depends on the time derivative, change of electric field. And with that term, you can say changing electric field produces magnetic field, and changing magnetic field produces electric field. This was Faraday's law. So this happens in 1865, and he goes through mathematical derivations of some of the kind of consequences of this new term. And he predicts what would be called electromagnetic wave, a wave of electric field and magnetic field. And this drawing is a little bit sloppy. I tried to fix it with the prompts, but it doesn't quite fix it, so let me redraw it. So I need to fix up this picture a little bit. Let me use this oscillating thing up and down. Let me say this is my magnetic field. And I think as this oscillates up and down, this is the place where I had to fix it up. This is all wrong because there's a visible discontinuity. Don't want that. But the magnetic field that's coming over here, crossing the equilibrium here, continues to oscillate, something like, let's say, crosses 0 here, oscillate 0 here, something like that. And this would be my magnetic field, my magnetic field. Then with this picture, electric field should look like this. Wherever magnetic field is crossing the axis, 0 point, that electric field should be crossing 0 there. So this oscillation looks like this, crosses 0 together here, and then oscillates and crosses 0 here together, and then oscillates, crosses 0 here again together, and then oscillates, crosses 0 here. Okay, that looks good, but then that is again messed up. Oscillates, crosses 0 here, and this would be like the electric field. And I'm trying to draw it in perspective view so that the electric field and magnetic fields are kind of perpendicular to each other. And then, so this would cross, something like that. So this electric and the magnetic field, they are mutually reinforcing wave oscillation of electric and magnetic field. And there are a few different properties that you can predict based on Maxwell's electromagnetic theory. One of the predictions would be this that I mentioned, that electric field cross product with the magnetic field using the right hand rule, that's parallel to the propagation direction. And that's why I labeled this as the electric field and this as the magnetic field. That way when you do E cross B, that gives you the direction of the thumb to the right, that's towards the propagation direction. So in 1865, Maxwell finally answered the question that must have been bubbling for 65 years since Young's double slit experiment. What is the thing that does the waving in the light wave? And so I guess to be technically correct, what Maxwell predicted is electromagnetic wave. Now the thing that's needed to make the connection that this speed of electromagnetic wave is the same thing as light is, well, the speed itself. So people measure the speed of light in those astronomical phenomena, and there were also other kind of terrestrial experiments that measure the speed of light directly. So by Maxwell's time, people knew that this is the speed of light, about 3 times 10 to the 8 meters per second. And when Maxwell made this prediction of electromagnetic wave, one of the result of the prediction is that it gives you the speed of the wave, and in the formulas it would be the speed is combination of 2 physical quantities, 1 over square root of the electric constant times the magnetic constant, permittivity of free space, permeability of free space. And when you plug in the numbers, you get a number that's suspiciously close to speed of light. And the kind of the obvious conclusion to draw there would be electromagnetic wave is light, or light is electromagnetic wave. So this is where we are at near the end of the 19th century, with Maxwell's prediction of electromagnetic wave. We have a formula for speed of light and how it connects to electricity and magnetism. And this is the triumph of the classical theory of electromagnetism, unifying two seemingly disparate forces, electricity and magnetism, and through that unification, giving us a better understanding of something that we have seen from time immemorial, and only very recently, within the last century, from the perspective of Maxwell, within the last century, understood as wave. Now we know what kind of wave it is. Now, as we wrap up this classical physics phase of this lecture, let me point out something. So this is what the slide is saying is the quiet fractures. But these equations are quiet contradictions. I think this is something that you can maybe look up and read about on your own. It's what's referred to as Lord Kelvin's two clouds lecture. I don't know if the original lecture is worth reading, because sometimes with the primary sources from hundreds of years ago, some of the scientific paradigm is very different from what we have today. But there are other people, more modern people, writing about Lord Kelvin's two clouds lecture, and that almost presciently kind of points out the two things that's going to be the start of the modern physics. And the first of those two clouds concern light still. So let me talk about the role of light in modern physics in the next part. So let's talk about the role of light in modern physics. We have this nice result out of Maxwell's theory of electromagnetism. And when you consider this carefully, it causes some problems. Let me go to the next slides to talk about that. It has to do with something we call relativity. And the idea of relativity, or principle of relativity, is a very familiar one. In fact, it dates from time of Galileo, who did a thought experiment of his times version that I'm going to describe right now. So in your daily experience, if you have any experience flying, for example, on a commercial jetliner, so on a commercial jetliner, the airplanes you might be riding in, that travels at something like, 600 miles per hour. And as you travel at the 600 miles per hour, I don't think you feel any different. I mean, when it's taking off and landing, then you see like a push into your seat, there's all that. But once it's at a cruising altitude, cruising speed, like if you went to sleep at the beginning of the flight and woke up in the middle, you wouldn't be able to tell if the airplane is still flying at 600 miles per hour or if it already landed. It just has the engines on for some reason. And that kind of sensation that you couldn't tell how fast you are moving without looking outside and looking at other things that'll give you relative speed. That feeling, so that's captured as a principle of relativity. One that says laws of physics, I will say, don't change with the speed. We usually say laws of physics are invariant with respect to change of inertial reference frame, but it just means laws of physics don't change when you are moving. Now, when you are accelerating, that's a little different, but when you are moving, not accelerating, then from that alone, you can't tell anything is different. There's no law of physics that will tell you how fast you are moving in an almost absolute sense. And with this principle of relativity, we have some kind of intuitive everyday experiences. For example, imagine the experience of throwing a ball. Let's say you can throw it at 10 miles per hour. Then if you're on the train, throwing a ball at 10 miles per hour, if you are imagining being an observer out here, looking at the thrown ball, then you would see, oh, the ball is moving at 70 miles per hour. That's the 10 miles per hour plus the speed of the train. Like that is your intuitive sense. Now, this intuitive sense runs into a problem when you try to apply it to light. So naively, you might think, light from my perspective, when I shine it, it moves at 300 million meters per second. So if I am moving with a train at 60 miles per hour, you might think the observer who's looking at this light wave will see the light wave traveling at the speed of light, see very large value, plus additional 60 miles per hour. That's what you would think intuitively. And that's the only way in which this principle of relativity makes sense, naively. Now, here's the problem with the speed of light. Unlike the speed of this ball, which, we could throw it at any speed, speed of light, we have a formula for that. The formula says speed of light is equal to 1 over square root of epsilon naught, or permittivity of free space, times mu naught, or permeability of free space. This formula, it follows from laws of electromagnetism, which means if we say that laws of physics don't change with the speed, then this is part of the laws of physics. So we should say this doesn't change with the speed, meaning as I'm shining this light where I am at the speed I am going, if I see this light moving at c according to that formula, the outside observer who's looking at this light too and observes this light wave moving, they would also say it's moving at c, not c plus some number. That's the paradox. The principle of relativity states that speeds are always relative to the observer and add up. That's your intuitive idea of relativity, what we today call Galilean relativity. But Maxwell's math says that the speed of light is an absolute constant that comes from other constants built into the fabric of reality. Yeah, that's Notebook-LM's phrasing. I don't know if I like that. So, but this is the important point. If light's speed is dictated by unchangeable laws of electromagnetism, then it cannot change with relative motion. This is the problem with the speed of light. And people try to resolve this. Some of the, if you want to read more, look up and read about something called luminiferous, I may not be spelling it right, luminiferous ether. And this is how Lord Kelvin worded one of the clouds he saw. It concerned the ether, how we are embedded within ether, and how the motion of planets is possible without affecting the ether and all that. And people actually try to detect the drift speed of ether, how fast we are moving relative to luminiferous ether, and that attempt gave a null result, meaning in trying to measure our speed relative to ether, they measured zero speed. So this is the first kind of trouble involving light. And it's very frustrating because it seems like we know so much about light, even having this comprehensive theory that results in this beautiful prediction of the speed of light. And instead of being happy with it, we are finding all these contradictions coming from it. And consideration of this is what results in special relativity. In fact, the Einstein's paper establishing special relativity, it's titled on the electrodynamics of moving bodies. So this problem is precisely what Einstein was looking at when he developed his theory, special theory of relativity. And there were some other experiments involving light that didn't yield quite well to being explained through our understanding of light as electromagnetic wave. And these are all, again, very frustrating and very tantalizing almost. Because once we say light is electromagnetic wave, it looks like we are saying so much about light. We understand a lot about electric field and magnetic fields. We understand their properties well through our electric and magnetic experiments. And in some sense, you might even say light is simple. It doesn't have a lot of complicated interacting parts within it. I mean, there are interacting parts within it, but they are all completely described by Maxwell's equations. You might say it's simpler than atoms making up elements. And with this simple but powerful theory of electromagnetism, one would think you can explain so much things, and you can, but as you are explaining so much things, not everything can be explained. So what this slide is illustrating is a phenomenon that's called photoelectric effect. And I guess there's no description of it here. So imagine this is a metal surface and you are shining light on it. Let's say this is red or even infrared, and let's say this is a UV light. And what people call photoelectric effect, it refers to the fact that as you shine light on metal, sometimes if a metal forms oxide layers, then you'd have to sand the paper off this oxide layer so that you can see this effect. And so people have done this experiment. They understood the different features very well. And as you shine this light, some electrons pop out of the metal surface. And in some sense, this is great because now that we understand the light as electromagnetic wave, it makes total sense that the light being incident on some surface would shake off some charged particles, and that those charged particles would escape like electrons having received enough energy. But as people investigated this phenomena, there were some features of it that was really hard to explain. And there were a number of them, but what I would say is the most important, hardest to explain part of this phenomenon is an existence of a threshold. So this light wavelength, if the wavelength was longer than a particular threshold, or you could say if the frequency was lower than a particular threshold, using the wavelength frequency relationship, then you wouldn't see this photoelectric effect. And I think I can understand how if the oscillation isn't happening frequently enough, you might say, oh yeah, the electrons, they are being shaken, but they are not being shaken enough to escape the metal. So, okay, but why couldn't you make it up by having a larger amplitude wave instead? Because even if you are doing it gently, almost like tsunami coming in and going out, you do it at large enough amplitude, it's gonna shake some loose things. But intensity didn't matter as long as the incident light was beyond the threshold, longer than a particular threshold or below a particular threshold frequency. Photoelectric effect simply didn't happen. And on the flip side, as long as you had a short enough wavelength, like UV, intensity actually didn't matter. With the less amount of intensity, you would still get electrons ejecting. Just not as many, but you would still get electrons of similar kinetic energy ejecting out of the metal, as long as the wavelength was short enough. And this is really hard to explain through the wave, electromagnetic wave model of light. And resolution of this paradox is what's going to lead to quantum mechanics. I'll leave that for Unit 4. Einstein also plays a role here as a theorist. And next of the curious things with the light that we would look at as the thing that motivates modern physics is what's called black body radiation or thermal radiation. This is again something that I have to describe it as tantalizing, in that you have this different pieces of physical theory. You have this microscopic model of matter with charged particles, electrons going around or associated with the proton. I think they discovered electrons by this point. I don't know if they had the model of this thing orbiting. So there's such a thing called thermal radiation, light that you get from things that are hot enough. Once it's hot enough, you will actually see that's visible light. But even at lower temperatures, you will feel that there's infrared radiation. And so you have that phenomena that you feel you could explain through these charged particles making a material. They are moving at some finite temperature, and because they are charged, they will produce some kind of an electromagnetic wave. So it feels like you have all the pieces needed to explain thermal radiation. You have some understanding of the makeup of the matter. You have some understanding of the radiation that would be emitted in some process. And there are problems in trying to piece this together. That problem is captured in what's called the Rayleigh-Jeans law, or classical prediction of thermal radiation. This is a theory, it works well enough at long wavelength. So this red curve would represent the theoretical prediction of Rayleigh-Jeans law. It says that if you go to a very long wavelength, then the wave intensity goes down. Kind of makes sense in that if you're not oscillating things quickly enough, then it won't radiate as much radiation. I think that makes intuitive sense. Now, this law would predict that as you go to short and short wavelength, the intensity goes up and up without limit. And if this were something that actually happened in reality, it's a catastrophe. Imagine opening a hot oven. It would have some thermal, infrared radiation that's in a reasonable amount. But as you go to visible and the UV, the intensity increases. So as you open that hot oven, you'll get blinded by a burst of visible light and UV. Opening a hot oven would blind you with a lethal burst of UV rays. That, of course, does not happen. What actually happens in experiment is represented by this blue curve. So as your wavelength gets shorter, initially there's an increase in the intensity, but at some point, that intensity begins to go down, so that at the very short end of this radiation, the intensity is basically 0. Now this shifts with the temperature. At higher and higher temperatures, it would look more like this, but the intensity eventually, so let me call this higher temp, but the intensity eventually dies down. And this is resolved in something called Planck law. And again, beginning of quantum mechanics, one of the two pillars of modern physics. And as you are trying to do the explanation, some of the things you can kind of excuse yourself for not fully understanding. There's talk about the oscillators and sometimes those material properties. Maybe you think it's just more complicated than we thought. Maybe there's bits and pieces of it that we didn't fully understand. That's why our theory isn't working. But when you look at the light portion of it, again, the electromagnetic wave is so elegantly simple. And what we are missing has to be more than simple little detail here and there that we didn't know. It's a more fundamental misunderstanding that has to be corrected through the modern theory. So at this intermission, this is where we stand. So having introduced the light as electromagnetic wave, we've described some things that's puzzling and would lead to the theories of modern physics that we are going to spend Unit 4 in. And as this says, these three experiments, they show that classical physics was incomplete. And I think to be completely truthful, a lot of physicists at the turn of the 19th, 20th century knew that. That's what drove the development of special relativity and quantum mechanics. So the classical electromagnetic wave theory could not, not survive. It could not explain these results. Now, it still forms the basis of what we are going to talk about in special relativity and quantum mechanics. It's the kind of wonderful thing about our scientific approach, is that even when we are wrong, we are not completely wrong because of our experiment-based approach. Even when we have a new theory, like special relativity and quantum mechanics, these new theories still have to replicate the results of the old theory. So, we'll still continue to use classical electromagnetic wave theory, but with the understanding where its limitations might be. And the reason I want you to tell this story of light is because I really feel light is what has been at the center of our endeavor in the modern physics. So, for example, QED stands for quantum electrodynamics. This is the study of interaction of light and matter, treated fully relativistically, where the matter, electrons, might be moving at speeds comparable to speed of light. And this QED is the complete theory of light and matter. And this is the crowning achievement of the 20th century physics, being completed in the, I want to say 70s, 80s. That's when the elements of what we call standard model of particle physics was being put together. And even up to today, this is one of the most precisely experimentally confirmed physics theory. That comes up in what we call, I guess, anomalous G factor of electron measurement. Long story short, naively, what we call this G factor should be approximately 2. And this is actually coming from relativity, but there are higher order corrections to it. So it's a 2 point ... bunch of digits. And there's a theoretical prediction using Feynman diagrams and all that. And there's an experimental measurement of this G factor. And they agree with each other to like a 7, 8 digits. And no other known result in science so far has such a beautiful and precise agreement between theory and experiment so far. So this is the crowning achievement of the 20th century physics. So at this intermission between classical physics and modern physics, I want you to take some time to reflect on how much we've been able to learn through light. Light began as humanity's first biological tool for surviving the immediate environment, running away from the predators and catching our prey. And through centuries, by the way, all these are, I'm pretty sure, all AI generated words, so I wouldn't exactly word them that way, but let me just read it. Through centuries of rigorous debate, false peaks, and paradigm shattering paradoxes, it evolved into our ultimate tool for decoding the universe. By trying to understand a simple beam of light, I'm not sure if accidentally is right, accidentally uncover the deepest, strangest truths of reality. And I do think there's a lot about physics that can be cast as study of light. That's why I wanted to tell this story of light. Thank you.